Hello, this is part 2 of line integrals, section 15.2, where we will mostly talk about a contour that is a segment in space or in the plane. So we will mostly do, I think, 2 of our 3 examples here are going to be in space, and then we will see one in the plane that's made up of 2 segments. So interesting, exciting stuff. So one thing that will be helpful when we do lines in space in 3 dimensions is to call the initial point t equals 0 and the terminal point t equals 1. We have to define bounds for t, so that makes the most sense to do it this way, and then to figure out what that parametric equation will look like, given that we actually know how to write parametric equations for lines in space. So we're going to keep that in mind. So t is going to range from 0 to 1 like usual. And then if I am writing the linear equations in parametric form, remember I would say x, y, and z are all that slope-intercept form, basically. So slope times t plus my quote-unquote y-intercept, which would essentially be my initial point. So in terms of x, my slope, my quote-unquote slope, will be the difference from t equals 0 to t equals 1. So 1t plus my starting point right here, which would be 1, or t plus 1. All right, and we'll do the same thing for y. It looks like a change of 2t plus a starting point of 1. For z, it looks like a slope of 0. Or I'm sorry, a slope of 1. 1t. I'll go ahead and write the 1 in there. You could just write t plus a starting point of 0. Okay, so that's my parametric equations, just remembering what that looks like for our lines in space. That was back in chapter 11, but I think we've reviewed it since then, so just keep those in mind. So just like before, we start by doing this to define our position r of t, which would be t plus 1, 2t plus 1, and t. And we do that so that we can figure out what our, and for this one, we are going to use our original formula. We're not going to do f dot dr. We're not asked to find work. So we are just calculating a line integral. So what that means is, we are converting our xyz squared in terms of our parametric equations, and we are converting ds using the magnitude or speed, if you'd rather think of it that way. So we're kind of going back to that original calculation that we were first doing. We are not doing the equation for work. So we will find our derivative here, which looks like 1, 2, 1. And then we will go ahead and calculate the magnitude of r prime, giving us the speed, or ds, if you will. And so for that, we get 1 plus 4 plus 1, so the square root of 6. And when we go to plug that in, we are just going to do the setup. Again, like in class, I trust that you can do the integration, so we'll just focus on the setup here. If I'm calculating the line integral, we are going to calculate that contour, again, defining t going from 0 to 1. We are going to convert our integrand here, xyz squared, using our parametric equations. So that looks like that will be t plus 1 times 2t plus 1 times t squared, since it's z squared. And then we have to multiply ds being equal to our magnitude of r prime, dt. So that looks like that's going to be the square root of 6 dt. And if I were to simplify before integrating here, and we can again leave out the integration, but I'd pull that constant to the front. I'd integrate from 0 to 1, And multiplying that all out and simplifying that a bit, I got, well, I got something different here. I feel like I should get 2t to the fourth, but I feel like I left something out in my notes here. Sorry, I'm doing this in real time here, but multiplying that out, I think I just did for the inner part here, 2t squared plus 3t plus 1. That would still get multiplied by a t squared dt. Not quite sure why I didn't multiply that through, but there you have it. You can do that if you're calculating the line integral. So that's example 1. The important part there being, how do we define our contour if we have a line segment in space? And it comes down to remembering our parametric equations for a line in 3D. So hopefully that part is helpful if you run across problems like that one. All right. So that's example 1. Well, what if our contour C is made up of multiple pieces? And so this is, like I had mentioned, this is the part where we have 2 segments. And so, maybe we get like a corner or something like that, but we're going along C1 from 1, 2 to the 0.34. And then we are picking up from 3, 4, and we're headed back down to the 0.40. So what we're going to do is we are still going to use our parametric equations to define our position vector. And we're going to just do that in 2 dimensions here. So with respect to C1, we would say that our x equation and our y equation would look like this. I can write that a little more clearly, but x is equal to 2t plus 1, and y is equal to 2t plus 2. And we're using the same principle that, this would be t equals 0, and this would be t equals 1, and that would make the most sense for us to travel from one to the other. Okay, and so we would set up with our position vector. And so I'm going to go ahead and do that. And, actually with this, we do have a little bit of a shortcut here. Now, the reason why, and I'll just point this out, this one is set up a little differently in my integral here. I have dx and dy, okay? This is actually a little hint and a clue that we can do something a little different here. So if I have C1 defined in such a way where x is equal to 2t plus 1, and I go ahead and find dx, and I'm deriving this with respect to t, it looks like I'm getting 2 dt. If I do the same thing for y equal to 2t plus 2, and I take dy, which would give me 2 dt, that I have a little bit of a simpler job here in setting this up because I don't have to replace a ds, right? Notice we didn't have ds, we had dx and dy. So those are what I'm looking to replace with something in terms of t. I can do that by taking the derivative of both those x and y equations of my parametric equations. So I can do my conversion actually directly here, where I say, okay, I'm going to convert my integral. I'm going to go from 0 to 1 because those are my bounds on t. And I'm going to rewrite this x times y. Since I know x is 2t plus 1, I'm going to multiply that by y, which is 2t plus 2. And that's going to get multiplied by what I found for dx. So that's going to get multiplied by 2 dt. And in addition to that, I'm going to add this second piece. So I'm going to take x, 2t plus 1, plus y, 2t plus 2. And I'm going to multiply that by what I found for dy, which is 2 dt. So look at that. I've converted without using that r prime because ds wasn't included in my original integral. So I'm using dx and dy to do that conversion. It's a little different, but it actually makes things kind of nice. You don't have to find as much information. So what I'm going to do, and you notice we're just doing this for C1. So what we'll do is the exact same for C2. So the answer to this question, what if C is made up of multiple pieces? Well, go ahead and figure out what it looks like along the path for C1. Do the same for C2, and then we're just going to add them together. Okay, so in order to find C1 here, I'm going to integrate from 0 to 1, and we'll see, hopefully, maybe I simplified this correctly. I think I get 8t squared plus 12t plus 4 for that first piece. And then for the second piece here, I think I got 8t plus 6. I'm just combining all of that and pulling the dt to the outside of that. So clearly we can simplify this a little bit further, but essentially, you would figure out what that equals, and that tells you what the line integral would be for C1 alone, okay? So this would be your solution on C1, and then we would go through and do the same thing for C2, okay? So same thing, you would define saying, all right, well, I'm going to start at some t equals 0 for this point, t equals 1 for that point, and go ahead and write the parametric equations and set up that line integral. And you can definitely do that as a little bit of practice here. You can speed through this part of the video if you want. I'm going to go ahead and write out the solution of what I got here for C2. So for C2, if you're kind of working this out, we could simplify that line integral so that, I believe what we are integrating, we pull the dt out here. This one I actually didn't simplify in my notes, but it looks like we get a negative 4t squared. We get minus 12 plus 4, so minus 8t plus 12, and then here it looks like I get a plus 12t minus 28, and pulling that dt to the end. You could simplify further here, obviously, and integrate that, but we would get some solution on C2, and then to find our overall solution, take what you got for C1, add it to C2, and that would give you your final answer there. For this one, if you're curious and you wanted to work it out just to make sure you got it, I got 22/3 for that. And, just as like little partial checks if you wanted to, for C1, I got 68/3. For C2, I got negative 46/3, and combining those was how I got the 22/3, okay? It's obviously good to make sure that you can do those. If you don't work through this example, but you do it on the assignment and you get it right, then that's fantastic. That's what we're going for. So our third and final example here is to find the work done on our contour C Again, we're doing a line segment in space here, but we are going to find work through a vector field. So this is combining our two ideas together. So now we are going to find work. Okay. Keep in mind that in order to find work, as we learned in the first part of 15.2, is we are going to integrate over C f dot dr. And that's how we're going to find that. So we do have f. We need to find our parametric equation in order to find r, and then go ahead and define f in terms of that same independent variable t. So let's go ahead and start with the position. We've got our segment here, so we'll call this t equals 0 and t equals 1 again. And the parametric equations, so I believe I wrote this out in class, that we need two things. The first one being f, that we are going to write as a function of r of t, so that essentially we have just that independent variable. And then given that we know r, that we would need r prime, because that is finding dr. Okay, so that's our ultimate goal. So finding r of t first. I'll go ahead and write out the vector function here for r of t. And that's what I get when writing that for each of those components to go from t equals 0 to t equals 1. So this would be r. We are going to go ahead and rewrite f so that it is also a function of t there. So x plus 2 times y. I'm going to go ahead and do that off to the side here. X plus 2 times y. Yeah, actually write that out. X plus 2 times y would look like all right. So it looks like we get a negative 8t plus 5 if we do x plus 2y. 2 times z, that's a little easier. So that'll be 4t plus 4. And then x minus y, a little easier as well. X minus y looks like 7t minus 4. Okay, so there's f. That's one of our needs. So we've got that. All right, dr, we need to find the derivative, r prime. So that looks like that will be 2, negative 5, 2. Pretty easy. Okay. Since we defined t as going from 0 to 1, again, anytime you have segments, that is probably the easiest to do. You know, that's kind of the key there. That's the nice part. Because now when we get down to our integral to find work, we're going to go along the contour from 0 to 1, and we are going to take f and we are going to dot it with the derivative of r. And, you know, when we did that, we took the derivative with respect to t, so that is dt, so we'll tack that on here to our integrand. And when we take the dot product, it looks like we are integrating negative 22t minus 18 is what I got when I simplified. Okay. And that's my integrand. And, we haven't integrated any of this because I've said all along, like, I trust that you can integrate this, and I do. But let's just go ahead and, work through this. And essentially what we get, evaluating it from 0 to 1, is we get negative 11 minus 18, and that gives us negative 29. So that is the work done through the vector field if we follow that path. So, hey, that might mean that, there's some vectors that are kind of pushing us along and helping us with that. And again, if you think of things like water flow and stuff like that, you would put forth negative work if, let's say, you're floating downstream. So essentially that's what's going on, and it's the net work done. So there may be certain points where you are doing more work, but you are essentially finding the net of all of the work that you've done to travel from 0 to 1. And that's the idea. So hopefully that helped. Let me know if you have any questions.